Welcome to This Explainer. Today, we are uncovering one of the most absolutely fascinating phenomena in the entire universe, quantum tunneling. It's a concept that completely defies our everyday common sense logic, yet it makes the modern world, and literally the stars shining above us, possible. All right, let's jump right in by asking the ultimate question that completely breaks our standard understanding of physics. Imagine you're facing a massive, towering wall, and you simply don't have the physical energy to climb over it. Classically, you are stuck, right? But in the subatomic realm, it's a totally different story. How do particles cross energy barriers that they classically shouldn't be able to overcome? Here is our roadmap for today's explainer. We're going to cover 1. The classical physics wall. 2. Enter the probability wave. 3. Tunneling through the barrier. 4. Powering the stars. And 5. Building the quantum future. Let's start with part 1, the classical physics wall, when energy just isn't enough. To really get this, let's start with a scenario grounded in the physics we experience every single day. Say you roll a ball with 100 joules of kinetic energy up a hill that requires 200 joules of potential energy to reach the top. The result is entirely predictable. The ball goes part of the way up, it runs out of steam, stops, and rolls right back down. The probability of it passing over the hill is exactly 0. But, and this is where things get wild, what is completely impossible for a classical ball rolling up a hill is actually possible for a subatomic particle. A quantum particle facing a barrier greater than its total energy actually has a non-zero probability of suddenly appearing on the other side. It doesn't climb over, it just passes directly through. So how does it do that? That brings us to part 2. Enter the probability wave, bending the rules of the universe. To understand how particles pull off this seemingly impossible feat, we have to completely rethink what a particle actually is. The crucial takeaway here is that our particle isn't just a hard, solid sphere like a tiny microscopic billiard ball. According to quantum mechanics, it acts as a wave function. Now, a wave function is defined over all space, and it determines the probability of finding that particle at any specific location. Because it behaves like a wave, its wave packet can spread out. And get this, it can actually be physically wider than the barrier it's hitting. I absolutely love this quote from IBM because it's such a great reminder. It says, quantum mechanics is a bit like the operating system of the universe. This bizarre wave-like behavior isn't some glitch in our physics textbooks. It is the fundamental code of reality. We're just finally learning how to read that code. Now, before we look at the barrier itself, we have to understand that this probability wave represents a really unique state called superposition. It's a quantum state where a particle exists as a weighted combination of all possible configurations simultaneously, at least until we actually measure it. It's this wild, multidimensional capability that allows the particle to explore physical locations that classical physics outright forbids. Let's move to the main event with part 3, tunneling through the barrier, the great escape. Let's break down the complex math of the Schrödinger equation into 3 clear physical steps, so we can see exactly how a probability wave filters through a solid wall. Step 1. The incident wave packet approaches the barrier in a potential-free zone. Step 2. Upon hitting the wall, the wave doesn't just instantly bounce back. A portion of it actually enters the barrier and undergoes exponential attenuation. Basically, that means the wave decays and loses amplitude the deeper it goes. But if the wall isn't too thick, we hit step 3. The transmitted wave emerges on the other side. A portion of the probability wave survived, meaning our particle has effectively tunneled right through. Now, obviously, not every particle makes it through. It's not a free-for-all. The exact probability of tunneling is strictly governed by 3 specific variables. First, you have the barrier width, or L. Second is the barrier height, representing the potential energy, labeled U0. And third is the total energy of the incoming particle, E. By adjusting these 3 parameters, scientists can precisely control how much of a quantum wave will filter through any given barrier. And you really have to keep in mind, this is an exponential relationship, not a linear one. The transmission probability drops exponentially as the barrier gets wider or higher. This matters enormously in real-world engineering because it means even a tiny, microscopic increase in the thickness of an insulating layer will drastically reduce the chance of an electron tunneling through it. Which perfectly sets up part 4, powering the stars, tunneling in the real world. You might be sitting there wondering, okay, why does this matter outside of a chalkboard in some physics lab? Well, without quantum tunneling, the sun wouldn't shine, and modern nanotechnology simply wouldn't exist, period. First up, we have radioactive alpha decay, which was a huge mystery until it was brilliantly solved by George Gamow using tunneling all the way back in 1928. Second, and incredibly importantly for us, is nuclear fusion in our sun. Particles in the sun's core classically do not have enough thermal energy to overcome their mutual electromagnetic repulsion, but quantum tunneling allows them to occasionally bypass that barrier, fuse together, and release the massive energy that literally sustains all life on Earth. We also harness this exact physics in scanning tunneling microscopes, which use tunneling electrons to image and even manipulate individual atoms. And finally, tunnel diodes are a totally foundational element in modern semiconductor electronics.
So what's next? That brings us to part 5, building the quantum future, harnessing the impossible.
Today, researchers aren't just observing this stuff. They are actively harnessing these strange quantum rules to build the next generation of supercomputers. To make quantum computers work, we rely on a concept closely tied to those probability waves we talked about: interference. Interference is the engine of quantum computing. By controlling how these quantum waves interact, researchers can effectively treat a highly complex problem like a giant maze. Through destructive interference, the probability waves cancel out the bad paths, and through constructive interference, they amplify the correct solution. But to physically build these machines, scientists have to cool materials down to near absolute zero. It's incredibly cold. These ultra-cold temperatures allow electrons to act as superconductors and form what are known as Cooper pairs. These pairs then quantum tunnel across physical insulators, creating a super crucial piece of hardware called a Josephson junction. This tunneling junction is the very beating heart of modern superconducting quantum processors. 100 million. That is a massive number. It's the amount of quantum gates IBM projects a system with 200 logical qubits will be able to run by the year 2029. By mastering phenomena like quantum tunneling and superposition, we are rapidly scaling up hardware to solve incredibly complex problems in chemistry and medicine, problems that would take classical supercomputers literally millennia to compute by brute force.
So think about this. If quantum tunneling already powers the stars in our sky, and the most advanced experimental computers here on Earth, how will the strange quantum world reshape your daily life next? I'll leave you with that thought as this impossible physics continues to unlock our future. Thank you for joining me on this explainer, and keep questioning the universe around you.